Welcome to the channel. In today's video, we're exploring the exciting world of retrievers in modern AI, the intelligent systems behind powerful search and information retrieval technologies. Whether you're building chatbots, semantic search engines, or retrieval augmented generation RAG applications, retrievers are essential for finding the most relevant information quickly and accurately. We'll dive deep into three main types of retrievers: sparse retrievers like TF-IDF and BM25 that excel at exact keyword matching, dense retrievers that leverage embedding-based similarity search to capture the true meaning behind queries, and hybrid approaches that combine both strategies to maximize precision and recall. You'll learn the pros and cons of each, practical use cases, and guidance on how to choose the right retrieval method for your AI projects. By understanding these retriever types and their architectures, you'll gain the tools to build smarter, faster, and more reliable AI systems that truly understand context and intent. Let's get started. What is a retriever? A retriever in AI is a specialized component designed to fetch the most relevant information from large data sets in response to a user's query. In the context of modern artificial intelligence, especially when working with large language models or retrieval augmented generation RAG systems, the retriever acts like an intelligent librarian. It doesn't try to answer the question itself, but instead finds the key passages, documents, or data points most likely to have the answer. When you interact with chatbots or AI assistants that can reference up-to-date facts or organization-specific documents, it's often a retriever working in the background. Retrievers operate using advanced search techniques, like semantic search, which compare the meaning of your query to the meaning embedded in documents, rather than relying solely on keyword matching. They turn your question into a vector and compare it to a database of vectorized content, efficiently finding passages that are contextually similar. Once the retriever surfaces these results, the generative AI model, such as a large language model, can synthesize the final answer using both its own internal training and the specific evidence provided by the retriever. This division of labor makes the AI more precise, reduces incorrect or outdated answers, also known as hallucinations, and allows the system to stay accurate even as new information becomes available without having to retrain the whole model. In summary, the retriever is a foundational AI component for building intelligent systems that need to ground their responses in trustworthy, real-world data. By connecting large models to up-to-date information, retrievers help create AI applications that are more reliable, transparent, and useful for practical tasks, whether it's customer support, enterprise search, or knowledge-driven chatbots. Let's discuss the definition and role of retrievers in modern AI systems like semantic search and RAG. A retriever is a vital component in modern AI systems designed for smart information search and retrieval. In the context of semantic search and retrieval augmented generation, or RAG, a retriever's primary job is to find the most relevant text passages, documents, or data points from a large knowledge base in response to a user query. Instead of matching keywords, a modern retriever uses advanced algorithms that understand the underlying meaning of your query, thanks to techniques like vector search and embedding models that turn both queries and documents into numerical representations. This allows the retriever to locate contextually relevant information, even if there are no exact keyword matches. In a RAG system, the retriever acts as the memory access mechanism for large language models, LLMs. When a user submits a question, the retriever first scans the knowledge base or vector database and pulls out the most pertinent documents or snippets. The LLM then uses this retrieved context along with its own world knowledge to generate a highly accurate, source-grounded answer. This dual process helps the AI provide up-to-date, reliable responses and dramatically reduces hallucinations. Those moments when a language model makes up plausible sounding but incorrect information. Retrievers are used everywhere you need smart, precise search, customer support chatbots, enterprise search, legal and medical research platforms, and any AI system where insights must be trustworthy and based on real data. They are the behind-the-scenes heroes that make systems like semantic search engines and retrieval-augmented AI both transparent and dependable for users. Now, time for us to understand the high-level architecture and how retrievers fit with LLMs and vector DBs. This is very important when you deal with any LLM models. Let's dive in. In modern AI systems that use retrieval-augmented generation, RAG, the architecture is built around three critical components: the user, the retriever, and the combination of a vector database and a large language model, LLM. Here's how they work together. After a user submits a query, the retriever first transforms this question into a high-dimensional vector using an embedding model. This vector representation captures the true intent or semantic meaning rather than just keywords. Next, the retriever searches a vector database where huge collections of documents or data chunks are already stored as vectors and finds those pieces of information that are most similar in meaning to the query. This targeted search is much faster and more effective than traditional keyword lookups. The retriever then selects the most relevant passages or snippets and passes them to the large language model. Finally, the LLM receives both the original question and the retrieved context-rich information. By referencing this fresh, specific content, the LLM generates a response that is not only fluent and coherent, but also grounded in real and up-to-date knowledge from the vector database. This cycle user query, vector search by the retriever, result handoff to the LLM, and AI-generated answer means that answers can keep evolving alongside the underlying data, reducing errors and staying accurate without retraining the whole AI model. This architecture enables enterprise-scale systems to combine the creative power of language models with the reliability of live data, powering highly accurate chatbots, semantic search, enterprise assistance, and more. I hope you have understood all the concepts discussed so far. Now let's talk about retriever types. Retrievers in AI come in three main types: sparse, dense, and hybrid, each with unique strengths and use cases. Sparse retrievers use classic keyword-based methods like BM25 or TF-IDF, turning text into very large but mostly empty sparse vectors, where the presence or frequency of each word in the vocabulary is noted. They excel at matching exact terms and are fast, requiring little training, but can struggle to find relevant results when users use different vocabulary than the documents. Dense retrievers, on the other hand, leverage machine learning models to create compact vector embeddings of text that capture deeper semantic meaning. This enables them to find contextually related information even when the words don't match exactly. Think connecting doctor to physician. Dense retrievers are powerful for understanding intent, but require more resources to train and may underperform if the task's domain is vastly different from the data used during training. Hybrid retrievers combine both approaches in a single retrieval pipeline. They simultaneously perform sparse and dense searches, then merge the results, typically using smart ranking algorithms. This gives hybrid systems the best of both worlds: the keyword precision of sparse retrievers and the semantic flexibility of dense ones. In benchmarks, hybrid retrievers consistently outperform their single-method counterparts, especially in complex or multi-part queries. Choosing the right type depends on your specific AI project. Use sparse for exact keyword searches, dense for semantic matching, and hybrid to maximize accuracy and relevance across a wide range of queries. Let's understand sparse retrievers in detail, which is a classic IR, TF-IDF, and BM25. Sparse retrievers, such as TF-IDF and BM25, are foundational classic information retrieval techniques used to identify relevant documents based on keyword matching. TF-IDF known as term frequency inverse. Document frequency calculates relevance by rewarding words that appear frequently in a document while penalizing those common across many documents. It is simple, intuitive, fast to compute, and works well for small or moderately sized datasets with uniform term distribution. However, TF-IDF lacks document length normalization, which biases it towards longer documents because they naturally contain more term occurrences. It also struggles with semantic understanding. Only exact keyword matches matter, so synonyms or rephrased queries are less effective. BM25 improves on TF-IDF by addressing these weaknesses. It introduces term frequency saturation, meaning repeated terms beyond a certain count add diminishing value to the relevance score. BM25 also normalizes scores based on document length, ensuring shorter but highly relevant documents are not unfairly penalized. This makes BM25 more robust and effective, especially in collections with varied document lengths. It is widely used in search engines due to its well-rounded relevance scoring. The pros and cons: both methods are computationally efficient and require no training. TF-IDF is easy to understand and implement. BM25 provides better ranking by handling document length and term saturation. Both work well for keyword-focused retrieval tasks. The cons: neither method understands semantics. Related but different words won't match well. Both can miss relevant documents if wording varies significantly from the query. TF-IDF can be biased towards longer documents. BM25 requires tuning of parameters to optimize performance. The perfect use case is sparse retrievers shine in applications like traditional document search, legal databases, and FAQ systems where queries are expected to contain specific terms. For example, researchers looking for exact legal terms or medical concepts benefit from TF-IDF or BM25-based search. However, for AI-driven applications needing semantic understanding or varied expressions, dense or hybrid retrievers are preferable. In summary, BM25 often outperforms TF-IDF due to its sophistication, but both remain vital baseline techniques for keyword-centric search problems. The next retriever is dense retrievers, which is mainly used for embedding-based similarity search. Let's dive in. Dense retrievers use embedding-based similarity search to find semantically relevant documents by representing both queries and texts as dense, fixed-length vectors in a high-dimensional continuous space. Unlike sparse retrievers that rely on exact keyword matching, dense retrievers encode the underlying meaning of text through neural networks, positioning similar concepts close to each other in vector space. When a query comes in, it is converted into a vector embedding, and the system calculates similarity scores, typically cosine similarity or dot product, between the query vector and stored document vectors to retrieve the most relevant content. This embedding approach enables dense retrievers to overcome the limitations of traditional keyword search, such as missing related documents with different wording or synonyms. For instance, a query about reducing server latency can retrieve documents discussing optimizing API response times because the semantic similarity is captured in their embeddings. Dense retrieval also effectively disambiguates ambiguous terms by using context around a query to clarify its intent. Popular dense retrieval implementations include bi-encoder architectures, where separate neural networks encode queries and documents independently, allowing efficient scaling. Advances such as pseudo-query embeddings and late interaction mechanisms improve retrieval accuracy, especially on longer or complex documents. The use cases is dense retrievers excel in AI-powered semantic search engines, question answering systems, recommendation engines, and retrieval augmented generation (RAG) pipelines, where accurate context retrieval is critical for language models to provide grounded, relevant answers. They are widely used in customer support bots, healthcare information retrieval, and large-scale document databases requiring nuanced understanding beyond keyword matches. The final one is hybrid approaches, combining keywords plus semantics for best precision or recall. Let's discuss in detail. Hybrid retrieval approaches combine sparse keyword-based and dense semantic-based methods to achieve the best balance of precision and recall in information retrieval systems. Sparse retrievers like BM25 excel in identifying exact matches for query keywords, delivering high precision by focusing on the presence of the specific terms users enter. Dense retrievers capture the semantic meaning behind queries and documents by embedding them into continuous vector spaces, enabling the retrieval of relevant content even when exact keywords don't match, thus enhancing recall by accounting for synonyms and context. By integrating these two methods, hybrid approaches address their individual limitations. Sparse methods may miss semantically related documents without keyword overlap, while dense methods can sometimes include less relevant results or generate noise. Often, hybrid systems perform separate sparse and dense searches and then fuse the results, using techniques like reciprocal rank fusion, RRF, to merge ranks effectively. Some newer models even unify sparse and dense embeddings in a single vector space or index to increase efficiency. The use case is hybrid retrievers are particularly valuable in complex domains like scientific literature retrieval, enterprise search, or large-scale question-answering systems where both exact terminology and conceptual understanding matter. For example, in medical research, a user querying heart attack treatment benefits from sparse search returning documents with those exact terms alongside dense retrieval fetching papers discussing myocardial infarction therapy, a semantically equivalent but lexically different phrase. This combined approach maximizes both the discovery of relevant, precise documents and the contextual coverage needed for deeper insights. Hybrid retrieval thus ensures higher overall accuracy, precision, and recall, making it the preferred choice in advanced AI-driven search systems and applications like Retrieval Augmented Generation, RAG, where sourcing comprehensive yet focused information is critical. Now we need to understand the practical guidance on when to pick which retrieval. When deciding between sparse, dense, and hybrid retrievers for AI-powered search systems, the choice depends on your specific data characteristics, query complexity, and operational requirements. Here's practical guidance on when to use each. Sparse retrievers, TF-IDF, BM25, when to pick. Choose when your corpus contains documents with well-defined, specific terminology. Users tend to search with exact keywords or known terms. Example: legal databases, scientific literature, FAQs. Resources or infrastructure for model training are limited, and you need a simple, fast solution. Interpretability and transparency of why documents are retrieved matter. The use case is a legal document search platform where lawyers search for precise terms like habeas corpus or amicus curiae. Sparse retrievers excel due to exact phrase matches and quick indexing without requiring extensive computational power. Now let's discuss when to pick dense retrievers. Embedding-based semantic search. Pick dense retrievers when your data includes varied or informal language, synonyms, or paraphrasing, when semantic meaning matters more than exact terms. Queries involve natural language or complex intent that keyword search captures poorly. You have sufficient resources to train or use pre-trained neural models for embeddings. You need to support conversational AI, customer support bots, or question answering systems requiring contextual understanding. The use case is a customer support chatbot that needs to understand user intent, fetching relevant troubleshooting guides even if customers phrase problems differently. Example, my laptop won't start versus computer won't boot. Dense Retrieval provides flexible semantic matching. Now let's discuss when to pick hybrid retrievers, sparse plus dense fusion. When you want to maximize retrieval performance with both high precision and recall, covering both exact term matches and semantic relevance. Your domain requires robust retrieval to capture all relevant documents, including those with different terminology. Computational resources allow running combined pipelines and advanced ranking. You are building enterprise search, scientific research databases, or retrieval augmented generation (RAG) systems needing comprehensive, precise context. The use case is an enterprise knowledge management system where employees search documents stored in various styles, formal reports, emails, and memos, using diverse vocabulary. Hybrid retrievers pull exact keyword matches alongside semantically relevant documents to provide exhaustive results. Choosing the right retriever hinges on balancing precision, recall, resource availability, and the linguistic complexity of your data and queries. Hybrid is increasingly preferred as infrastructure improves, but classic sparse and dense methods remain valuable for specific scenarios. To conclude, sparse, dense, and hybrid retrievers each play critical roles in modern AI-powered search and information retrieval systems, offering unique strengths tailored to different use cases. Sparse retrievers like TF-IDF and BM25 rely on exact keyword matching and excel when queries use specific, well-defined terms, making them ideal for legal documents, scientific literature, and situations requiring interpretability and fast indexing without training. Dense retrievers, powered by embedding-based similarity search, capture semantic meaning and context, enabling retrieval of relevant documents even when keywords differ. They are essential for complex natural language queries, customer support bots, and RAG systems where understanding user intent matters. Hybrid retrievers combine the precision of sparse methods with the semantic flexibility of dense embeddings, delivering superior recall and precision by merging their complementary outputs. This approach is especially valuable in enterprise search, scientific research, and diverse knowledge bases where comprehensive and precise retrieval is critical. Choosing the right approach depends on factors like data domain, query style, available computational resources, and desired accuracy. Sparse methods offer simplicity and speed, dense methods provide nuanced understanding, and hybrid systems strike a powerful balance, increasingly becoming the go-to for building reliable, scalable, and intelligent AI retrieval pipelines. Understanding these retriever types unlocks the ability to design smarter AI solutions that connect users with the most relevant information, no matter the complexity or vocabulary variation of their queries. Thank you so much for watching this video. If you found this content helpful and want to stay updated on the latest in AI, vector databases, and retrieval techniques, please make sure to hit the like button and subscribe to the channel. Don't forget to click the notification bell so you never miss our future videos packed with valuable insights and practical guides. Your support helps us create more high-quality educational content tailored just for you. If you have any questions or topics you'd like us to cover, please leave a comment down below. Thanks again for being part of our growing AI learning community. See you in the next video.